dynamic choices. So without further ado, Xiaosheng, the screen is yours.
Thank you so much, Francesco, for the invitation, and your colleagues as well. And thanks to Shaowei for being a panelist. It's actually been a while since I did my last presentation, but it's great to see a lot of you here. So this is a brief overview for the talk. I'm going to give some motivation for the exercise, and then I'm going to define the central object of study in this paper, which we call monotone additive statistics, as in the title. I'm going to present a main technical result that characterizes these objects, and then sketch a proof of this characterization for you. And then finally, in the last part of the paper, last part of the talk, I'm going to discuss in detail an application of this of these statistics to stationary time preferences. So, as a quick motivation, let's sort of go back to some of the micro that we all studied back then. So, as a lot of us know, CARA expected utility has a special property that it is independent of the agent's wealth level, meaning that the preference that the agent has between two lotteries does not change does not change depending on the wealth level at which these lotteries are evaluated. And more generally, its CARA expected utility is in fact independent, is invariant to any independent background risks that the agent might face. And that's a simple that follows simply from the fact that these preferences are wealth independent, and then these preferences are expected utility, so they satisfy the independence axiom. So just to make this notion of wealth invariance more formal, I'm going to say that a preference over lotteries is invariant to wealth or to background risks if whenever we have three lotteries X, Y, and Z, where Z is independent of X and Y, then X is preferred to Y would imply that the independent sum X plus Z is also preferred to the independent sum Y plus Z. So here the interpretation is that X and Y are the lotteries that the agent wants to compare, and Z is an independent source of background risk that the agent can take into account when making this comparison.
Xiaosheng, can I ask you a question?
Yeah, go ahead.
Yeah, so how do you think about the following question? So I think one issue with CARA is that people don't think that the decision maker's preference should be invariant to background risk, right? So for example, when your wealth level changes, the risk attitude may change. And but of course, I mean, finance people, they still use CARA because of its tractability and so on. It's not that CARA is totally a bad model, but I just wonder how you guys think about this.
No, I completely agree. I think the part of the, as I was sort of talk about in a bullet point down below, part of the motivation for thinking about this is to make it useful for maybe estimating risk preferences, where CARA is widely used because of the tractability, right? Even though we know that oftentimes people's, as you said, people's risk attitude does depend on the wealth level, making the sort of the extreme assumption enables the researcher to focus on other aspects of the estimation. So this is, sort of thinking about, I'm not saying that this is necessarily a desirable property, but I'm trying to explore, right in the next bullet point, I'm going to say that I'm trying to explore what this property would theoretically imply, and whether we can get something, slightly more general than CARA that might be useful for some exercises that empirical researchers might want to do.
Got it. Thanks.
So yeah, so it can be shown relatively easily, and I think it's a well-known result, even though I don't I don't know an sort of an exact reference for this result. It might be a sort of Folk's theorem kind of result that within expected utility, only CARA preferences have this property of being invariant to the agent's wealth level or independent background risk. But the question we want to ask is, what if we don't restrict the preference to be expected utility? So in theory, one could ask, so in theory, the property of being invariant to background risk is an independent property from the preference satisfying the independence axiom. So if we don't impose the independence axiom that would lead to expected utility, what kind of preferences would we get that are still invariant to the wealth level? And as I said in answering Shaowei's question, one reason we might care about this is that CARA expected utility has been widely used for preference estimation, for example, but maybe the CARA framework is too rigid to fit search and choice behavior. And by thinking about what other non-EU preferences may have the wealth invariance property, we can try to see if we can fit those choice behavior better. Okay. So how do we go about answering this question of what general preferences are wealth invariant? So I'm going to make a kind of a simplifying assumption here that the preference emits a certainty equivalent, which means that for every lottery X, we can find a constant phi of X that is indifferent to X under this preference. This is a simplifying assumption, but it is not really a strong assumption. For example, it is guaranteed if we impose some continuity assumption on this preference. So then the question would become, what properties does this certainty equivalent phi need to satisfy in order for the associated preference to be invariant? So let's take two independent lotteries X and Y and denote their certainty equivalents to be phi X and phi Y. So by definition of the certainty equivalent, we have X is indifferent to phi of X. Okay. Now we listed on the top of the slide, we have the wealth invariance property, which means that if we think about if we plug in phi X as the Y here, then X is indifferent to phi X implies that X plus any independent Z is indifferent to phi X plus any independent Z. And if we plug in Z to be Y, which we assume to be independent of X, then we get X plus Y is indifferent to phi X plus Y. Okay. By a similar reasoning, from the fact that Y is indifferent to phi of Y, we can substitute out the Y's in this indifference condition with phi of Y and maintain the indifference. So at the end of this, we get Y plus phi of X is indifferent to phi of Y plus phi of X. And combining these two indifferences, we will get that X plus Y is indifferent to phi of X plus phi of Y. Okay. So the upshot of this quick analysis is that the certainty equivalent of X plus Y has to be phi of X plus phi of Y if the preference is invariant to independent background risk. So to summarize what I just said, for any invariant preference, the certainty equivalent mapping phi has to satisfy this identity, where for any independent lotteries X and Y, the certainty equivalent associated with their independent sum is equal to the sum of their individual certainty equivalents. This is a necessary condition for the preference to be invariant, but it's also easy to see that if the certainty equivalent satisfies this additivity condition, then the preference will also be invariant. So it's actually necessary and sufficient. So now, of course, at this point, we don't know what such a certainty equivalent mapping phi has to look like in order to satisfy this additivity condition, right? And this is exactly what our paper is going to answer.
Xiaosheng, a quick question.
Yeah.
So X, Y, and Z, they are one-dimensional, right?
They are one-dimensional. Yes, they're
It has to be one-dimensional.
Okay. So that's a good question. The results that I'm going to present can generalize to multidimensional lotteries. So like these are random vectors instead of random variables. There is a somewhat natural generalization, but I think for the ease of discussion, it's better to just think about one-dimensional random variables.
Yep. Thank you.
Okay. So with that motivation, I'm going to get into the formal definition. So I'm going to say that a descriptive statistic, or statistic in short, is a way to summarize every random variable by a number. So you can think about this as the certainty equivalent mapping phi. But there are other familiar descriptive statistics. For example, the median of a random variable is a way to summarize random variables by a number, or the expectation of a random variable. Just to make it a little more formal, I'm going to use L infinity to denote the set of all bounded random variables on a fixed non-atomic probability space. Here, the boundedness does matter for the results. If you're interested, I can talk more about that later. So a statistic is going to be a mapping phi that maps these bounded random variables to real numbers. And here I'm going to impose a normalization condition that every constant random variable is simply mapped to the same constant, simply summarized by the same constant. So any certainty equivalent mapping is going to satisfy this normalization condition. The median is also going to satisfy this normalization condition. Okay. Since we're studying monotone additive statistics, let me describe to you what I mean by monotonicity and additivity. I'm going to say that a statistic is monotone if for any two random variables x and y that are ranked in first order stochastic dominance, then the numbers we use to summarize these random variables are also ranked in the same way. Okay, and just as a reminder, first order stochastic dominance means that if we take any cutoff c, then the probability that the first random variable is bigger than c has to be at least as large as the corresponding probability for the second random variable. Okay, so that's what I mean by monotonicity. And one particular corollary of monotonicity is that this mapping phi, this statistic, depends only on the distribution of the random variable, but does not depend on where exactly on the underlying probability space that this random variable takes a particular value. Because any two random variables that have the same distribution will first order stochastically dominate each other, and therefore their statistic value has to be the same. Okay. Next, I'm going to talk about additivity, which was already alluded to earlier in the introduction. I'm going to say that a statistic is additive if for every pair of independent random variables x and y, the statistic associated with x plus y is equal to the sum of the statistics assigned to x and to y. And so the main technical question that this paper is going to answer is, what are the monotone additive statistics? Before I get to the answer, I'm going to first talk about a few examples or non-examples. A non-example is the median, which is monotone, but it's not additive. However, the following examples are all monotone and additive. The leading example would be the expectation. And in fact, as we all know, the expectation is additive for any pair of random variables, even if they're not independent. And in fact, there is a converse to the statement that I just said, which is that if we do impose a stronger form of additivity for every pair of random variables, then it has to be the expectation. And this was a classic result due to definity. And it basically means that in order to get something beyond the expectation, we necessarily have to relax additivity. Okay? The way we relax it is to only impose it for independent random variables. We do get something more than the expectation, and an example would be the maximum of the support. To see that the maximum is additive, let's imagine that one lottery has a best possible payout of $20 and another lottery has a best possible payout of $10. Then it's clear that the sum of these two lotteries cannot ever pay more than $30. But $30 is also, in fact, possible because these two lotteries are independent. So there is a positive probability that the first lottery pays $20 at the same time as the second lottery pays $10. Okay, so the maximum of the sum of these two lotteries is exactly the sum of their maximum. Symmetrically, the minimum is also going to be a monotone additive statistic. And in the next bullet point, I'm going to introduce a family of these examples that embed the previous three. They embed the expectation, the maximum, and the minimum. And this family is the CARA certainty equivalents. So these are the certainty equivalents defined for a given CARA preference. So to give a little more detail, let the parameter A denote a particular CARA agent's level of risk seeking. Then the CARA utility would be exponential with a parameter A in the exponent. The expectation of e to the ax is this CARA agent's utility for a lottery x. If we take the log of that and divide by A, we get to the certainty equivalent that this CARA agent finds indifferent to the lottery x. And this CARA certainty equivalent, which we denote by Ka of x, is clearly monotone because CARA preferences do like more money than less, but it's also additive. The algebraic reason why it is additive is because these expectations, which are called the moment generating functions, are multiplicative for independent random variables. But economically speaking, the additivity of these CARA certainty equivalents is closely tied to the fact that CARA preferences are independent of the background risk, as we discussed at the beginning. So we have a whole family of examples of monotone additive statistics that are indexed by parameter A, which denotes the agent's denotes the CARA agent's level of risk seeking. And to see that this family embeds the previous examples, we will have to take a certain limit. If we take the limit as a goes to 0, then essentially we're thinking about a risk-neutral agent. And the certainty equivalent for a risk-neutral agent is precisely the expectation. So K0x is equal to the expectation of the lottery X. Similarly, if we think about an infinitely risk-loving agent, which corresponds to A going to infinity, then such an agent is so optimistic that she would consider evaluate every lottery by the maximum possible payout. And so as A goes to infinity, the CARA certainty equivalent is going to converge to the maximum of the support. Symmetrically, the minimum of the support is the limit as A goes to minus infinity, corresponding to an infinitely risk-averse agent.
Can I ask a question?
Yeah.
Feel free to postpone the answer, assuming this is a reasonable question, to the end, because maybe this belongs to the end. But you mentioned, first of all, these are the moment generating functions, and we know that the moment generating function, the name itself says it has a relationship with moments of a distribution. So
yeah,
not just the mean, just about any moment, right? So I wonder whether there's something to that, and which brings me to the variance is additive, but it's not monotone in the way that you define monotonicity. But maybe if you define monotonicity with respect to something like second order stochastic dominance, then I'm not sure, but maybe it would be monotone in that sense. So I wonder whether higher moments and things like that also could be incorporated in this kind of way of thinking about these frameworks. I don't know whether
that's a good question.
Sensible question. Yeah.
Let me table that question for a little bit after presenting the results. But it's a great question about the variance. As you said, the variance is additive for independent random variables, but it is not monotone with respect to first order stochastic dominance. It's still not monotone with respect to second order stochastic dominance because second order stochastic dominance actually allows more things to be comparable than first order, right? Variance is only going to be monotone if we restrict attention to random variables that have the same mean, and maybe ask for monotonicity in the mean preserving spread order. So I can talk a little bit about that once I get to the results. Yeah, but that was definitely a great question. Yeah. Okay. Good. So we have now seen a one-dimensional family of examples of monotone additive statistics. It's natural to ask if there's anything beside these CARA certainty equivalents. The main result of our paper is going to say that these are basically everything, except with the twist that we can also take weighted averages of these different CARA certainty equivalents, because taking weighted averages does not violate monotonicity or additivity. So the formal theorem is going to say that if phi, a mapping from random variables to real numbers, is a monotone additive statistic, then it can be written as an average of different CARA certainty equivalents. So if we want to think about phi as the certainty equivalent for a certain agent's preference, one interpretation for this preference, this utility representation, is that the agent may not be sure about his or her risk aversion level. She first puts herself in the shoes of a particular CARA agent and evaluates and calculates the certainty equivalent of the given lottery under the assumption that she has that particular level of risk aversion. But after doing that for every possible level of risk aversion, she will aggregate these certainty equivalents to obtain an overall evaluation of the lottery.
Xiaosheng, may I ask you two questions?
Yeah.
Right. So the first one is, so when X is multidimensional, how do you do the CARA certainty equivalent calculation? So that's the first one. And then the second one is, oh, maybe you can do it, do the first one first.
Sure. So good. So when X is multidimensional, there's no sort of there's no CARA in that space. But these moment generating functions can be generalized to multidimensional things, right? Instead of A times X, we can consider A1 times X1 plus A2 times X2 for two parameters A1, A2. And it turns out that because the moment generating function, even in the multidimensional case, is still multiplicative, these sort of pseudo certainty equivalents are still going to be additive. And they're monotone if A1 and A2 have the same sign. So the corresponding results for two-dimensional X would be essentially the same, except that it's an integral over these two-dimensional A's that have coordinates that have the same sign.
And the second question is the following. So you made a normalization assumption at the beginning,
Yes.
right? So if you drop that one, it's not going to affect this much, right?
Yes, so it would just change the probability measure mu to be any positive measure. The result remains intact. Basically, once you fix the value of phi of the constant 1, right, it fixes the value of phi for every constant because of additivity. And so that's really just a normalization.
Got it. Thank you.
Yeah. Okay. Good.
Can I ask a short question?
Yeah, go ahead.
Just to understand if I understand. So mu is the first time that appears here, and it says there's a unique mu. So is there an interpretation of that? Is this, it's not linked to the original distribution, is it preferences?
So it's so it's inherent to the preference. So for any preference, if we think back on the original motivation about a preference that's invariant to background risk, then for every such preference, it's associated with a different mu. When mu is degenerate, it's a point mass, then the preference is standard CARA.
I see.
But this is saying that we can, in some way, somehow sort of combine different CARA preferences without violating Wells invariance, without violating the invariance property.
But those weights, do they mean something if it's not degenerate?
Well, it's sort of like how likely does the agent think that he's risk averse versus risk loving, right? You can think about it that way.
Okay, thank you.
So Xiaosheng, let me ask you a question. If I restrict attention to just constant random variables,
sure,
then the additive restriction is just Cauchy's functional equation, right?
Yes.
And Cauchy's functional equation has a unique solution if we assume some sort of continuity or at least also monotonicity is what's giving you
right
uniqueness here. Okay.
So the way you can think about it in that case is if we have phi of 1 equals 1, let's say, then phi of every integer is equal to that integer, and phi of every rational number is going to be equal to that rational number. And so for any real number, you can bound it above and below by rational numbers. You can approximate it that way. And so monotonicity can serve the same role as continuity in Cauchy's functional equation.
I see. Got it.
Yeah, but it does also suggest that, if we, one question that we often got is, what if we drop this monotonicity assumption in the problem, right? One would easily see that we can replace this measure mu by a sign measure and still preserve additivity, but we actually don't have that kind of a result because of issues related to what you were just saying. Yeah.
Xiaosheng, can I just ask, in the interpretation of this uncertainty equivalence,
Mhm.
I mean, what is this kind of preference? How does this kind of preference over lotteries relate to known non-expected utility preferences over lotteries in the case where mu is non-degenerate? I mean, there's a few sort of standard things, right?
Right. So, well, it's hard. It's not. I think it's the closest one. I would say the closest preference that I know of to this class of preferences would be the cautious expected utility preference.
Yeah.
Where instead of averaging certainty equivalence, what they did was taking the minimum of a bunch of certainty equivalents.
Yeah.
They didn't restrict to CARA preferences in the family.
Yeah.
Right? So there is a, I think the connection to that paper is the closest. And in terms of the, axioms, there's also a superficial analogy because their paper has sort of a invariance property when you mix with a constant, right? Whereas we are thinking about independent sum with a constant. So Wells invariance is not mixing with a constant, but actually adding that constant to the lottery. So there is a superficial analogy in the axiomatization as well. But I don't think there's I haven't figured out a deeper connection yet. Yeah.
Thanks.
Yeah. Good. So let me make a couple of quick comments about possible extensions of this result that may be of interest, and I'll make use of some of these when I get to the applications. So one natural question to ask is, what if we don't have this statistic defined on all bounded random variables? Maybe it's only defined for integer random variables or non-negative random variables. And the reason this might be of interest is because if we're dealing with time preferences, then time is non-negative, and in some cases we want to think about time as being discrete. So for those settings, perhaps the mapping phi is only defined on a smaller class of random variables. But I just want to assure you that exactly the same result would hold if phi was only defined for on these smaller domains. And the reason the result remains intact is because it's not hard to show that any monotone additive statistic defined on those smaller domains can be uniquely extended to one that's defined for all bounded random variables. So with that step of extension, we can basically show the same result for those smaller domains.
But sorry,
what is
the statement then that these are the only ones, or is the statement that these are the only ones if you also insist on the axioms holding when you do extend to the full
No,
domain?
These are the only ones if you just have monotonicity and additivity on that smaller domain.
Okay, great. Thanks.
Yeah. That's thanks for the clarification. Yeah. The problem becomes actually more interesting and more difficult if we want to go beyond bounded random variables. In our applications, we're not going to do that, but perhaps this could be useful for some exercises. So let me briefly talk about the extension to that case. So one immediate issue is that for unbounded random variables X, perhaps these CARA utilities or CARA certain equivalents are not even finite to begin with. So what we can show is that if we restrict to those unbounded random variables that have these finite CARA utilities, then essentially the same result still holds. So in other words, as long as we restrict attention to random variables that have sub-exponential tails, we can still characterize monotone additive statistics defined on that larger domain. Okay, I'm not going to talk more about the extension because it's a little more involved than the proof that I'm going to give you for the base case. Yet another direction that one can extend this result is to change monotonicity to perhaps monotone with respect to second order stochastic dominance, which was what Francesco suggested. And as I said in my quick answer, because second order stochastic dominance actually allows more comparisons than first order stochastic dominance, it's more restrictive on this statistic phi. And so if we require the statistic phi to be additionally monotone with respect to second order stochastic dominance, then we need to sharpen the result to say that the measure mu is supported on the negative A's. So the interpretation of this is, if we want the preference to be second order stochastic dominance monotone, then we're saying that this preference is risk averse. And the only way that an average of CARA certainty equivalence is risk averse is when every single one that goes into the average is also risk averse. Okay, the negative A's correspond to risk averse CARA. And so the result here in the last bullet point is saying that if we have a additive and second order monotone statistic, then it has to be an average of the risk averse CARA certainty equivalence.
So can I bring it back to what you said to me, which I'd forgotten, but it's true. If you impose that random variables have the same mean, then you can just look at certainty equivalent. So if I'm correct, if I follow the logic, then you go back to the whole support for mu. Is that what you're saying there?
No,
you could have risk loving. You could have mean preserving increments or something like that, right?
Right. So let me now answer your question. First, perhaps reiterate your question to make sure I didn't get it wrong. So you asked, what if what about the variance? Like, can we get variance as sort of a statistic that satisfies some nice properties, right? Because it's already additive. So one exercise we can do is to ask to look at random variables that have mean 0 or whatever fixed mean, and think about additivity defined in the same way. Actually, mean 0 is better because additivity requires the sum to still have the same mean. So let's look at mean 0 random variables, and let's impose that this statistic, this mapping defined on these random variables is additive for independent ones, and it's also monotone in the mean preserving spread order. Okay, that's going to allow variance to be a feasible statistic in this sense. And in fact, it can be shown that the only ones that are monotone and that are additive and monotone with respect to mean preserving spread are given by these. So these are, because second order stochastic dominance, covers mean preserving spread, these statistics will still satisfy that version of monotonicity, but these actually don't include the variance. All we need to do in order to get those statistics that are monotone with respect to mean preserving spread is to throw variance into the bunch. So basically, a statistic on those mean 0 random variables is additive and monotone with respect to mean preserving spread if and only if it's an integral of these risk averse CARA certain equivalents plus a constant times the variance. So that's a result that we don't actually include in the paper, but we have a sort of separate nodes that actually shows that result.
Sorry, to fully understand. So phi of x must look like this expression here plus constant times variance.
That's right.
Okay.
That's right. Okay. I'm going to, okay. I have 20 minutes. Okay, let me quickly give a proof sketch for this result. And the result is going to depend on a key lemma, which I think may be of independent interest. The lemma says that take two lotteries x and y, such that every CARA agent strictly prefers x to y. Then we can find an independent lottery z, such that the sum x plus z stochastically dominates y plus z. So in words, if every CARA agent prefers one lottery to another, then we can find a level of background risk that makes the first lottery stochastic dominant and therefore preferred by every monotone agent. You might ask, why do we need KAX bigger than KAY in the precondition of the lemma? The answer is that these conditions are essentially necessary for such a level of background risk to even exist. And that's because CARA preferences are independent of background risk, as we discussed. Right? In order for x plus z to stochastically dominate y plus z, x plus z must be preferred to y plus z by every CARA agent. But CARA preferences are independent of the background risk z, so x must be preferred to y for every CARA agent. Okay. And what the lemma says is that essentially these CARA comparisons between x and y are also sufficient for such a background risk to exist. Going to skip this example and quickly tell you how we prove this lemma. Basically, we constructed Z as a truncated Gaussian density. I'm going to simplify the discussion here by just taking Z to have a normal distribution without worrying about the truncation. So what we want is that x plus z stochastically dominates y plus z. I'm going to let f and g denote the CDF of x and y. And x and y have bounded support, so we can assume that f and g are supported on some interval minus n to plus n for some large n. In order for x plus z to stochastically dominate y plus z, we want to find a density h, which is the density of the random variable z, such that the convolution between g and h is everywhere larger than the convolution between f and h, because these convolutions are the CDFs of y plus z and x plus z. Okay? And stochastic dominance is ultimately a comparison of CDFs. So the way to construct such a z is we take this h density to be a Gaussian density, okay, with a large enough variance. If we calculate the difference between these convolutions, it comes down to this integral on the second line here, which I have highlighted with the red part and the blue part. The blue part, when the variance v is sufficiently large, is going to be approximately 1. Whereas the red part turns out to be equal to the difference in CARA expected utilities between x and y after a integration by parts. Okay, so because we assume that this CARA difference between x and y is positive for every level of risk aversion, we get that the red part is going to be positive, and the blue part is going to be the integral of the red part is positive, and the blue part converges to 1. So that gives a not entirely rigorous proof that we can construct this background risk Z to create stochastic dominance between X and Y. Now let's see how this lemma would imply the representation in the mean theorem. So monotonicity says that if X stochastic dominates Y, then X has a higher statistic. If we combine it with additivity, we get that if X stochastic dominates Y under any background risk Z, then X has to have a higher statistic than Y. Okay, and the reason is because from this stochastic dominance, we get that phi of X plus Z is bigger than phi of Y plus Z by monotonicity. But by additivity, we can decompose phi of X plus Z and phi of Y plus Z as phi X plus phi Z and phi Y plus phi Z separately. Okay, and canceling out the phi Z, we get phi of X is bigger than phi of Y. So from the first bullet point to the second bullet point, we're basically weakening the precondition. Right? Now the lemma tells us precisely when the weakened precondition can be satisfied. We can find such a Z to create stochastic dominance between X and Y if and only if every CARA agent prefers X to Y to begin with. So if we put all of this together, if every CARA agent prefers X to Y, then X has to have a higher statistic value than Y. The rest of the proof is going to use some functional analysis techniques. Basically, we're going to define for every random variable X, we can define a function L of X that takes as input the level of risk aversion and outputs the certainty equivalent at that level of risk aversion. Once we have these functions, we can think about phi of X not as a mapping from random variables to real numbers, but instead as a functional that maps these functions to real numbers. Because there's a one-to-one mapping between random variables and their LX functions and their certainty equivalence from. This functional is going to be monotone precisely by this statement. So if L of X is bigger than L of Y at every point, then the phis are also ranked in the same way. This functional is also going to be additive because both this mapping phi and this function L of X is additive for independent random variables. So we have a monotone and additive functional defined over these LX functions, and we can extend it to be a monotone additive functional over all continuous functions, which allows us to use the Reed's representation theorem. And that's going to give us the integral representation in the main results. Okay. So in the last couple of minutes of the talk, I'm going to talk about our main application, which is to stationary time preferences. And here we're going to revisit a classic paper by Fishburne-Rubinstein, who axiomatized exponential discounting in on a domain that involves pairs of that involves what we call data rewards. So data rewards is a pair xt where you receive x dollars at a future time t. Fishburne-Rubinstein considered preferences on this domain, and under some standard assumptions, they showed that the key axiom of stationarity, which I'm highlighting right now, is equivalent to exponentially discounted utility. So stationarity says that your preference between two data rewards is unaffected if these data rewards are pushed into the future by the same amount of days. So to take an example, if you prefer $10 today to $100 a year from now, stationarity requires that you prefer $10 a year from now to $100 2 years from now. And the main result of Fishburne-Rubinstein's classic paper is that these axioms imply that the preference is represented by an exponentially discounted utility where there is a utility function u on the monetary reward, and it's discounted exponentially according to the time at which the reward is going to be received. What we're going to explore in this paper is how does this representation generalize to a slightly larger domain when we allow the time at which the reward is going to be received to be random. So in this part of the paper, we're going to consider what we call time lotteries, which is a pair x capital T, where for simplicity, we're still going to fix the reward x, but we're going to allow the time t to be random. So for example, this could correspond to a traffic route where you will always get to the same destination, but the time at which you get to it depends on the route you take, and it's random. Or it could be an investment project that has an uncertain date of return. So we're going to consider preferences defined on this larger domain and explore the consequence of stationarity. So we already know that on the smaller domain where there's no uncertainty about either reward or time, stationarity implies exponential discounting. On this larger domain, we're going to impose a similar form of stationarity where your preference between two time lotteries is unaffected if they are delayed by a common random time, as long as the common random time is independent from the original time lotteries. So this is a certain strengthening of the original stationarity axiom, but we show in the paper that it can be related to time invariance and a certain form of dynamic consistency in our setting. I'm not going to, for the interest of time, I'm not going to talk about that in much detail, but this relation to dynamic consistency can be found in the paper. What we show is that stationarity does imply exponential discounting, but with certain twists. So we show that any monotone stationary time preference has sort of an exponential discounted utility representation where there's a monetary utility u of x and it's exponentially discounted. But in the exponent, there is a phi mapping that maps every random time t to its certainty equivalent. And this phi mapping has to be a monotone additive statistic in order for the preference to be stationary. So written this way, it might look...
Xiaosheng?
Yeah.
Xiaosheng, a good question. So let me see. So suppose you allow x to be different, right? So for example, with some probability, you're going to get x and t. And then with some other probability, you're going to get y and s. And how would your theory be extended to that kind of domain?
Right. So there needs to be some additional axioms imposed in order to characterize the implications of stationarity. One way you can get a representation in the larger domain is to say that there is independence across different outcomes x. but within the same outcome, there may not be independence over t. I'm not sure if does that make sense? So meaning that sort of there's a two-stage process by which you evaluate that kind of lottery. You first look at every fixed reward x and look at the random times at which you will get the reward.
I see.
You apply this utility representation, and then you take an expectation over different x.
Right. So essentially, you're gonna impose a subjective ordering about how you're gonna look at these the uncertainty, right? So you first, for conditioning on every realization of the price, you look at the time, and then you look at the. I got it.
Right. So to actually sort of turn it into axiom, it will be something like independence over x, but not joint independence.
Yeah. So then in that case, I think you're turning this domain into a little bit like a two-stage Crash-Proteus kind of domain, right? And so therefore the full independence is not supposed to hold.
Right. Even though, I mean, x and t, they're not naturally ordered, so it's not. But it has that spirit, I guess. Yeah, it has that spirit. So written this way, it may look a little complicated, but actually what it is if we think about phi t as a as an average of these CARA certainty equivalents, when we turn to the domain of time preferences, these CARA certainty equivalents becomes the certainty equivalents for expected discounted utility preferences. So what this representation is saying is that the agent first finds the certainty equivalent in the shoes of different expected discounted utility agents, and then averages these certainty equivalents, and then apply exponential discounting to their averaged certainty equivalents. Now, why do we care about such a generalization? There are at least two reasons. One is that it shows there are multiple ways to extend exponential discounting to time lotteries while maintaining stationarity. We're familiar with the expected discount utility representation, but it's only a special case. And this flexibility actually allows us to explain certain behavior that are not allowed by expected discount utility. For example, risk aversion over time, which I'm going to talk about, is something that's not possible within expected discount utility, but it is possible within a larger framework. And there's a further application that I don't think I'll have time to talk about, but it's regarding the aggregation of different discount factors, which relates to some of the work that Shaowei did. But let me go relatively quickly and perhaps just spend 1 or 2 minutes asking you to think about these choices, these hypothetical choices that will hopefully illustrate the flexibility of our preferences. So I'm going to, let's consider two choices where the reward is fixed to be $1 million. In the first choice problem, you can either receive this money after 1 day, or you can receive it immediately with 99% probability, but with 1% probability, you get it after 100 days. Okay, notice that the expected time at which you will receive the reward is the same across these two options. But the first option is risk-free, while the second option involves a small chance of a long delay. I think it's plausible to choose the first option because it allows us to avoid the small chance of having to wait very long. But now let's consider a second choice problem where the date at which you receive the reward is kind of flipped, in the sense that the first option now gives you the reward after 99 days for sure, whereas the second option gives it to you right now with 1% probability, but with 99% probability, it gives you after 100 days. So once again, the expected time at which you will receive the money is the same across the two options. But now the second option may seem more appealing because it gives you this small chance of avoiding a long wait. Okay. So if an agent simultaneously chooses option, the first option in the first choice problem and the second option in the second choice problem, then this agent would be risk averse in the first choice problem because the expected time of the reward is same across the options, but he's choosing the safe option. But then in the second choice problem, he would switch to choosing the risky option. So this agent would be sometimes risk averse, but sometimes risk seeking, depending on the particular lottery ahead. Now, this cannot really be explained by the familiar expected discounted utility preference, which is always going to be risk seeking because exponential discount factors are convex. But what we show is that our preference representation can explain this kind of mixed risk attitudes towards time. Okay, I think I'm over time, so I'm going to pause and take questions.
Okay.
Can I?
Shaowei, I was just going to say, please, if you have any questions, go ahead.
Okay. So your example is very similar to the fourfold risk pattern, right? And so I wonder if now you look at losses, right? Mm-hmm. So would you exactly see the flipping kind of behavior?
Well, this is I've not done an experiment on this. We think these choices are reasonable, and we've asked during some talks we asked people what they would choose, and these seem like predominant choices, but we've not.
I think the choice behavior here is completely sensible. I just wonder, suppose now you make X say minus $1 million, and then in that case, I think according to the fourfold risk pattern, I would anticipate that people's choices will be flipped, right? So
yeah,
and then this will be also consistent with your theory, right?
That's right. In fact, it's actually easier to see that it's consistent with our theory because flipping the reward to the negative sign is essentially changing your wealth level. But our preferences are independent of the wealth level. So sort of flipping, if you flip the reward to be minus 1 million, then the first choice problem essentially becomes the second choice problem. And so necessarily the choices will be flipped.
Okay, thank you.
Shaowei, anything else?
I think someone else is asking a question. Right?
Yeah, so Omer is actually raise your hand. Please go ahead.
Hi, sorry, Xiaosheng. Just a question about the convex order. So if you take the positive CARA ones, when you take that integral, you're integrating it against a convex function, right? So I think that should also be monotone, maybe in the wrong direction.
You mean in the mean preserving spread order?
Yeah, if you take the mean preserving spread over zero mean random variables, I'm a bit confused because I understand what you said, but then, right, if I look at the risk seeking CARA agents, their certainty equivalent it's maybe anti-monotone, right? Maybe the negative of that should also be a monotone additive statistic, like the variance. But I'm sorry that I'm you were not prepared for these questions, and you're getting them thrown at you in real
Good.
time. Which
No,
is hard,
well, yeah, we should discuss that. Well, it's that's a good observation. I on the spot, I'm probably too slow to answer that, but let's discuss that afterwards.
Okay, I'm sorry.
Yeah. No, that's a good question. Yeah, you might be right.
Anybody
you might
else?
be right. Yeah.
Sorry. Anybody else? You don't need to raise your hand or anything. Just unmute yourselves. Okay, I have a question which is probably I already know the answer to, and I think it's the obvious question. I mean, Shaowei brought this up at the beginning, which is this issue of constant absolute risk aversion being maybe convenient as a functional form, but not seeming to represent really this idea that risk attitudes ought to depend on underground risk, in risk or wealth in the background. So, but here the functional form as basically an exponential seems to be very important. So what about constant relative risk aversion, which clearly doesn't have an exponential functional form? Is there no hope to be able to do an exercise along the lines of this with those? Or is there's hope, it's just much harder?
Well, I think there's an easy way to translate this result to the setting of constant relative risk aversion. We just, for every lottery, we just need to take the log to think about the sort of the return, the percentage sort of increase. Think about everything in terms of percentage increases. And so I think once we transform the problem in this way, it will lead to an analogous result that says, I think it would be, if it's monotone and additive, if we require the statistic to be additive when you multiply two random variables, then it's an average of constant CRRA, certainty equivalence. I have to write it down to make sure the details are right. But I think
phi of x times y equals phi of x plus phi of y. That's what.
Yeah, right. So basically, you think about x and y are like, percentage returns, like percentage increases. Mm-hmm. Then I think there's a one-to-one mapping between CRA and CARA.
Maybe it is obvious to other people. My feeling would be that if you write a version of the paper, I would like that point to be made. I don't know whether it's being made in the current version, but
no, that's a good point. I don't think we make it, but I think it would be good to include that point. Yeah.
I mean, now that you explain it, that taking of logs, that seems natural, but it wasn't that obvious to me ex ante. Okay, fair enough. Anybody?
That's great. Yeah.
Anybody else has questions? Okay.
Xiaosheng, I have a somewhat more technical question. I wasn't sure whether it's a good idea to ask it here or not, but since nobody else has a question, so maybe let me try it. So in the Riesz representation theorem part,
yes.
So I remember. Right. So could you bring up that slide?
Yeah.
Okay, so it looks very, of course, mathematically they're the same thing. So it looks very similar to a Hassani kind of aggregation result. But then I remember there's a paper by Zhou Lin. What he said is the following. So the Hassani's result only applies to finitely many different preferences. Here, you basically saying, imagine you have a population of all these CARA people, and they have different CARA parameters. And then the Pareto condition is going to hold, right? And I remember in Zhou Lin's paper, when you're dealing with infinitely many agents, it's got to be a compact interval so that you can have the additivity, the integration kind of representation. Otherwise, you can only have finite additivity or something like that. But you don't have this problem here.
No, well, so first, because I think the settings are somewhat different. Harsanyi's aggregation result is for expected utility things, for expected utility preferences. And here, none of these, well, even though the individual CARAs are expected utility, if you think about the phi as representing a preference, it doesn't have to be expected utility. And in fact, in order to aggregate the individual CARAs into this phi, we have to first take the certainty equivalence of the CARAs instead of directly averaging their utilities. So I think on this space, it does look, yeah, there definitely is a connection to Harsanyi's theorem, but because it's non-expected utility, I don't think the restriction there would apply here.
Okay.
Yeah.
Okay. I guess we had a couple of minutes more to think about more questions if anybody has any. Okay. I think there are no more questions. We can stop